What's up, everybody? Let's talk some more about these electric fields and electric field lines. We've taken a look at these formulas for point charges or charges in space, charges in free space. And let's talk about some math that we can do with this. So we're talking about electric field intensity, okay? Or the magnitude of the electric field. And we're going to use the letter E, okay? Now, let's say we have a pile of positive charges here, a pile of electrons, okay? And they are obviously going to be sending out an electric field 90 degrees to the surface here, emanating into free space in all directions. Everybody agree with that? Okay. Now, what would happen if we put a little positive charge right here, a little positive charge right there in the field? This is positive, and that's positive. What's this thing going to do? It's going to go away. Does that make sense? So when we're talking about this little guy right here, we're talking about just like a positive test charge. So this thing's always going to have a charge of 1.6 times 10 to the negative 19th coulombs. So in the situation I'm talking about right now, this charge is always the same thing, okay? Now, if we want to measure the electric field intensity right here, the electric field intensity, we're going to use a formula called E is equal to KQ over R squared. Sorry, I hit the camera there. So this Q stands for the charge of the sphere or the ball of charge. It's not this. This is a test charge. It's a positive test charge, so we're just always talking about a proton here. So the electric field intensity, this close to, all right, well, let's see, what is this? We're going to say this is the nucleus of an atom, all right? And the nucleus of this atom may have a charge of something like, I don't know, 2.4 times 10 to the negative 17th coulombs. I think that's a pretty reasonable guess for the total charge of the nucleus of an atom. And so this charge right here is 2.4 times 10 to the negative 17th coulombs, and this is a test charge. And if we're wanting to measure the electric field intensity at this point, this distance away from this charge, we would say E is equal to KQ over R squared. So the electric field intensity is equal to K, which is 9 times 10 to the 9th, times Q. Q is the charge here, the charge of the ball of charge or the nucleus, whatever you want to call it. 2.4 times 10 to the negative 17th coulombs. And the distance, all right, so these distances, we're talking about a nucleus. If we were this far from the center of the nucleus, let's say it's, I don't know, 8 times 10 to the negative 15th meters, all right? Now that's got to be squared. And you're like, Mr. Perkins, these are very, very small numbers you're giving us. Yep. We're talking about the electric field around the nucleus of an atom, so of course these numbers would be small. So I'm going to let you at home do this math here. Okay, let's see what you got. Now I'm going to try it. The electric field intensity is equal to 9 EE9 times 2.4 EE17 negative, divided by, and I'm going to put this in parentheses, 8 EE15 negative. Then we have to square that, and then boom. So the electric field intensity here, we get a number that is 3.38 times 10 to the 21st. And you'd be like, okay, Mr. Perkins, I can do the math, but what does that mean? This means 3.38 times 10 to the 21st, let's look at our units up here, coulombs per meter squared. That will be your units. You're like, well, those are some weird looking units. It is, but this is the intensity of electricity per meter squared of surface area if you're this far from this charge and you're a proton. You're like, gosh, this really seems like some weird stuff. Well, you'll be asked to do some problems like that. But you may be like, why would you be talking about having a charge near another charge? Well, one of the ways that we really do this is it really helps us think about batteries. Now, let's build us a battery here. I got a battery. Here's one plate of a battery, all right? And then we'll draw another plate of a battery down here. Okay. Now, we know that a battery, like a car battery, is a stack of parallel plates, right? You should already know that at this point in time. Well, we're going to say this metal plate in the battery, we're going to consider it to be positively charged, right? Or it's a good electron acceptor. And then this other plate of the battery, right, we're going to consider it to be negatively charged or something that can easily get rid of electrons. And in this space in here, right, and all this space here in the middle, we have a nice conductor of electricity, something like maybe battery acid. Now, so if these are parallel plates here, parallel plates, and they're charged, we can think of them in many different ways. We can think about these being parallel plates in a DC battery, or we can think, hey, we've got this plate and this plate hooked up to a battery. Like maybe these two metal plates are hooked up to like a 12-volt battery here. Okay? We can think about it like that. So if there's 12 volts of potential difference between the positive and the negative plates, then now we have a number. We've got a number to work with. We've got volts. So volts here is 12. Now let's do something here we haven't done yet. Let's go back and let's think about the direction of the electric field. It always goes in the direction that a proton would move. So if you're a proton and you're in this battery, you're within the two parallel plates of this battery, would you go up or down? Yep, you're going to go down. So first thing you need to know about electric field lines is they're straight and they're 90 degrees to the surface and they're going from in the direction a positive charge would move, okay? Now we know really electrons would be moving that way, but we always draw it in the direction that a positive charge would move. And as long as you're not here over near the edge, you get over near the edge, funky stuff starts happening, okay? So forget about that. We're in the middle of the plate. As long as you're in the middle of the plate, boop, 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 you're good. Now let's look at a way we could measure the electric field intensity in this plate. Here's a really good formula that's I don't think this one's even in your tables, but it's a common sense formula. The electric field intensity between two parallel plates can be measured in volts per distance. So the voltage difference between the two plates and how far apart the two plates are. Don't you agree that if we got these plates closer and closer and closer, the electric field would be more intense, or an electron would be more likely to jump across to the positive side if we got closer, right? When you get shocked by static electricity and you reach out, you don't get shocked from a long way away. You usually get shocked as you get closer. Well, it's the same thing. If you move parallel plates closer together, then the electric field intensity increases. So you can measure the electric field in volts per meter in between two parallel plates. Here's another thing I want you to think about. What if we took an electron right here? What if we took an electron, and this is something that's spoken of often in electricity. We took an electron and we tried to fire it through these two plates. What would happen? Well, the electron's negative, so what would happen is it would curve, whoop, towards the positive plate. Does that make sense? It would curve, and if we knew the voltage and the distance between these two plates, or the electric field intensity, and we knew the velocity of this electron, we could definitely predict where this electron would impact that parallel plate. Now, this is some technology that's used in a cathode ray, and this is some of the technology from the original televisions. So here are some things we just talked about with these parallel plates. One, the direction of the electric field, as always, is drawn in the direction a positive charge would move. The field lines are straight. As long as we're away from the edge, everything is nice and neat and uniform. The electric field intensity between parallel plates can be measured in volts per meter. And if we fired an electron through there, it's going to move towards the positive charge. Now, we might not be firing electrons through there. We could fire other charged objects, and they would also curve as well. What if we fired an alpha particle through there? An alpha particle is a helium nucleus, but it's missing electrons. It says a charge of +2. If we fired an alpha particle between two parallel plates, it would actually curve and go down to the negative plate, wouldn't it? So those are some things to think about when we talk about parallel plates. Here is a penny battery. Do you think this is an example of parallel plates? It absolutely is. You have two different metals. In this particular penny battery, we have pennies and aluminum. And then we have a little cardboard that we soak in vinegar, a little cardboard between them to facilitate the movement of electrons. So a little battery like this is parallel plates, and we could use the same math formula right here. We could use E is equal to V over D. And I want to hit one last point here about batteries and how we think about them doing work. I'm going to draw a parallel plate just for the heck of it. This time I'm going to draw up and down, all right? So we've got two parallel plates here. They're very different. And we're going to say that this is part of a 6-volt battery system, okay? And we know that the electric field intensity can be measured in volts per meter. And I'm going to make this the negative side. We're going to make this the positive side. And if I ask you to draw the electric field in here, you would draw it in the direction a positive test charge would move or a positive charge would move. Does that make sense? Now, we can use batteries to do work. Don't you agree with that? And work is measured in joules. All right? So how does this formula, and knowing we have a 6-volt battery, how does this formula take us to how much work a battery can do? Well, one thing, let's say this is, we're going to hook this up. We're going to call this 6 volts here. All right? One thing you need to know is batteries work by moving electrons, right? So the movement of the electrons is what gives the battery the ability to do work. We have electrons in one place. They want to go to another place. So in other words, the energy is stored in the battery. What is another word for storing energy? Yes, potential. Another word for stored energy is potential energy. So batteries have energy stored in the form of charge. Now, guess what? Remember what we talked about voltage was? I've called voltage the whole time. I've called it the potential difference, right? And now you're going to see that come into play. Work is joules. The electric field intensity between these plates is equal to the voltage between the plates, which is 6 volts in this case, and the distance they are apart. So we can just give this, these are 5 millimeters apart. So we'll just say this is 0.005 meters or 5 millimeters, right? So the electric field intensity between these two plates would be what? 6 volts divided by 0.0005 meters. So 6 divided by 0.0005. Wow. The electric field intensity here would be 12,000 volts per meter. 12,000 volts per meter. All right. What does that mean? Let me show you what it means. Here's our formula. E is equal to V over D. Well, what is a V? V is a joule per coulomb. What? 1 volt means that 1 joule of work can be done for every coulomb of charge. So if you have a coulomb of charge move across this battery, a coulomb of electrons move from the negative to the positive side, then 1 joule of work will be done if this is a 1 volt battery. This is a 6 volt battery, isn't it? So a 6 volt battery would do 6 joules of work if we had a whole coulomb, which remember is many, many, many electrons, like 7 billion electrons. If we had an entire coulomb of electrons move across this 6 volt battery, then 6 joules of work would be done. So a 6 volt battery does more work with the same amount of charge than a 1 volt battery does. So if we think about this, this is why we use higher voltage batteries. They can do more work. There's one last way to think about this. What if I had an electron over here, right? And I wanted to move it back. If I move the electron back, and remember, this is not the way the electron wants to go. This is not the way it wants to go. The electron wants to go from negative to positive, right? Because it's attracted to the positive. But if I moved an electron back across here, I would have to do work to do that. I would have to do work to recharge this battery to put the electrons back here. Does that make sense? So for every coulomb of charge where I move the electrons back, if I moved a whole coulomb of electrons back to the negative side of this battery, then I would have to do 6 joules of work to get that done because it's a 6 volt battery. So if you plug this in to a recharger, the outlet will have to do 6 joules of work for every coulomb of charge to recharge this battery. So that's the end of parallel plates.